Hello everyone, I hope you are healthy. Thanks for being here, and thanks Alex for organizing this wonderful event. I'll be Canadian once again this year, and I'm gonna say I'm sorry for my accent. I will do my best not to be too annoying with it. The goal of this presentation is to nudge more people toward proper and useful risk management methods. It's an introduction, and hopefully something that will show you some tricks, including what to do when you don't have all the data you think you need. We'll tackle building a model, why you need a real Monte-Carlo simulation for your risk. We'll talk also about beta distribution and a few other distributions along the way. It may sound like modeling is a nearly mythical experience where you need to have a firm grasp of arcane mathematics and hermetic financial models to do simulation. Well, it's just not the case. I'm not one of those gifted souls, that's for sure. But I'll try to simplify this as much as I can and show that with a little bit of work, everyone can get started and do some modeling. Because what's our role as risk management specialist or professional? Well, first, keep the board and the auditor happy. But then what's the other goal? Maybe the one with the best business value. It's to help inform decisions that are considering risk. And you need to do some modeling or to use some mathematics at the back to be able to do that. It forces you to challenge your assumption. It forces you to put some thinking and your thoughts into it while you're trying to understand your problem. Maybe the risk analysis is only one of the factors you need to consider while you take a decision, but it's a fairly significant one. So we'll do a quick recap on Monte-Carlo simulation, see how they work. Then we're gonna get starting with models, how to tackle the task of breaking down a problem and building a model. And also we're gonna talk about how to deal with when you have too little data or not as much data as you'd want. You need to remember that simulations are to be used when you don't have certainty on the outcome. If you knew perfectly how the world would go, you wouldn't need a risk analysis. You just put in the number in the spreadsheet and you take this to the bank. People that are pushing for single value deterministic models often forget that it's easier to come up with a range rather than just coming up with specific point. You got a lot more chances of getting it wrong if you're just providing information for a certain point. For example, here's a simple model: revenue, operating costs, and operating income. So if you know exactly those numbers right ahead, yes, there's no risk about it, but then you see in the future. Really, the world looks a little bit more like this. You've got a wide range for revenues and another range for operating costs, and as such, your operating income will vary depending on what you have. And there's not that many companies that are honest enough to contemplate this types of possibility that you could not break even, for example. Not something people like to put in financial plans, but it's just reality. So this is where running a model is superior than just the type of matrix heat map type of risk assessment. So the goal of today is to show how you can apply the thinking of a model to just about any business problem. For this demo, I could have used a budget. I could have used the production of widgets, but this is boring. It's been done many times. We could have used a model for COVID, but once again, I'll leave that to the pro because biostatistics is a very specialized area of work. So I could have taken a look at construction project, but there's probably 2-3 other people that will take that example for Risk Awareness Week. So let's tackle something lighter. So let's demonstrate how you can stay out of jail by using model risk from David Vos. And we'll try to make a profit out of it. So basically, we'll try to answer the age-old question: when you're stealing a jewelry shop, should you go for a daring smash and grab operation, or be more meticulous and go for safe cracking, sneaky in the dark? Quick note, the guys on the left are actual criminal. The guy on the right is not a criminal, he's from a TV special. So you see what I did here? I did my own little risk analysis for this webinar, and I'm mitigating my liability risk, making sure that I don't call someone a criminal who's not. Modeling forces you to think things through, and if you're honest and you have the right people around the table, and they answer truthfully, and we'll talk a little bit about psychology later, it will provide you with valuable insight about your business. So a typical risk assessment: let's say I'm a crook and I want to plan my next heist, try to get some money. Typically, I do a risk assessment like most corporations do. I could just write out what's my risk of getting caught while I'm doing the deed, and what's my risk of not having enough cash after the heist. So basically, those are the risks that maybe I've identified. And a lot of solution provider will tell you, well, you then put this within some sort of heat map, and this is a very basic one, from something could happen, very likely, or something is not very likely to happen, and it can be not very bad or very bad. I'm simplifying things here, but no matter if you're putting it in a 3x3, a 4x4, a 5x5, a 10x10 matrix, no matter if you got 2, 3, 4, 5, 10,000 colors, it doesn't change the fact that those are bad. And there's a lot of speakers to Risk Awareness 2019 and probably Risk Awareness 2020 who have proven that risk heat map, risk matrix are not a good way to take a look at decision making. So I will not redo the whole argument here. I will leave that for the others. But basically the only good heat map that you could have would be one that would have an infinite number of likelihood and an infinite number of potential categories of consequence with overlapping of those boxes, and then basically you got a Monte-Carlo simulation. So you don't need to, this is not something that's going to help you to take a better decision. Let's start with our objectives. If we're to do some modeling, we need to understand what are our objectives, what we're trying to accomplish or to do. And for that, so in this case, keep them in mind and make sure you have a hierarchy, so they're organized. You know which one is the most important, because at some point you might have to do trade-offs on those objectives. Especially as you start digging deeper by doing your simulation, you'll get insights, and maybe you'll understand that some things are more important than others. So you need to know, out of all your objectives, which one are the top priority ones. So here are my objectives in this case for my heist. I want to get 150 grand. I want to stay out of jail, and I want to stay alive. Well, those are not exactly very a good organization. Let me rephrase that. And my objective would be to stay alive, stay out of jail, and get the cash. As you see, I'm risk adverse to some things. Staying alive is more important to me than getting 150 grand. So this is why I flipped it around, because my priorities were just wrong. So once I've got my objectives, I know what I'm after. I'll need to break down my problem and understand it step by step. There's multiple ways of doing so. If you're working on a budget or a financial model, well, you already have that broken down according to revenues, expense, tax, amortization, and all those values. So you already know about that. In some other case, you might need to pick other tools from the toolbox, because once again, risk management is a pretty wide family of tools and methods and techniques. So you might just want to pick up the right one for what you're trying to do. There's nothing wrong, actually it's actually very good to take tools from other portion of risk management. And here I'm going to start with taking one which is a layer of protection analysis, which you see mostly in process safety. So basically a layer of protection analysis is when I take a look at something to happen, something good or bad, and then I'm doing the breakdown of all the controls layer that I have that are preventing that thing to happen. Typically that'd be done in a chemical plant, for example, or on a pressure vessel or something like that. So you need to see those controls then as successive lines of defenses, each adding to the overall risk reduction, so how much I'm trying to reduce the risk, as long as the controls are independent. So that's something to keep in mind. And the opening of Hubbard's first Failure of Risk Management book states such an example where the controls were not independent and led to an awful situation. I didn't read yet his second book. It's still on my pile of book to read, but his second edition. So I will see if he keeps that example. But it's a very good book that any risk management professional or financial professional should be reading to get a clear picture of what's real risk management. So getting back to my layer of protection analysis, that's something that could be done for just about anything. Yes, we use it in process safety, so for safety of chemical process a lot, but it could be used on the controls to prevent fraud. It could be used on, if you're at war and you're in the military, the defense layer that you have of minefield, barbed wire, everything you put in between you and the enemy so he can't rush you. So you could do something like that. So you got your criminal, you got your pay, the loot, what you're trying to get out, and then you got the different layers. So each one of those layers are like a protection. The building outer layer, wall, doors is the first step, first line of defense. The second line of defense would be the alarm system. So if you penetrate the building when you're not supposed to, you trigger the alarm and calls the police. For example, so that's another layer. And reinforced displays is another thing that you put in place maybe to prevent someone from just smashing and grabbing the jewelry, and then you get random patrols. And each of those lines of defense actually got some efficiency. And I'm just putting random number here, but it's just to show that each of them by their own will not prevent the heist. But together, they're making the cost of the heist so high, or so either by being too dangerous or limiting how much loot the person will grab, that by doing so, it creates, it will prevent the robbery from happening. So that's the way of breaking that down in that case, because once again, some risk management is purely arbitrary. Like it's something that's going to happen, it's random, a random process, so something will break at a certain point in time. You know the relative likelihood of that happening, but you don't necessarily know exactly when, but it's not something that someone will make happen. Here in this case, we're talking about a model of someone who's pitting his brain against another person. So you're someone that's trying to prevent your controls from working. So that's an interesting difference, and that's something you'd see in business as well. And there's another workshop on game theory and as part of Risk Awareness Week 2020, and I suggest you go and you pay attention, because a lot of risk management works when it's not someone who's actively working against your control, but a lot of business problems actually are. So based on that layer of protection analysis, we'll take that, and when we do the demo, we'll use those layers to identify the risk and the reward of doing various types of heist. But to do that whole workshop, you need to do the facilitation. And how do you do this? The first thing is you need a clear scope. You need to know what you're trying to analyze, and this is the first step to try to define, okay, I'm doing my scope is to evaluate on one side if I'm doing for example, a smash and grab, or I'm doing the more stealthy approach of going at night and being silent about it. So you need to have the scope of what you're doing the analysis, what are the objectives. So that's the first step. Then you need to get the right quorum, and quorum is who I'm putting around the table. You need people in that case. I think that for any risk analysis, you need to have people with skin in the game. I highly recommend Taleb's book, Skin in the Game. You want that people are committed to a real outcome and a useful outcome of the process, that they don't have too much bias, but that if they get it wrong, they'll suffer for it. So it's kind of important, I think. Then, so in our case, we'd want people that are going to commit the robbery. You don't want all external persons. Wouldn't want to give too much information about that heist to too many people that are not involved. You need subject matter experts, internal or external. Maybe the heist sponsor, if there's one. I think the police would make a great devil advocate in our case if we're planning a robbery, but I would tend not to bring them to the table for that specific risk analysis. But their insight would have been interesting, so maybe find a crooked cop. So that's the first step. You gotta have the right people, and then you gotta gather the data where possible, any data that's useful, and communicate it. Things like the average police response time in your city would be something interesting to communicate. The model of the alarm system, doing a reconnaissance to identify the other controls, for example, to see what are the types of reinforced bars that are on the windows of that jewelry shop. So those are all data points which would be useful and will help people evaluate the various risks. So that's something you can communicate ahead. You got to make sure that the information you have is right. Then it pays to explain the nature of the simulation. So make sure that the people around the table, they do understand the task, the expectation. What do you expect from people when they're sitting in one of your workshop? And make sure that they are in the right mindset. So there's a lot of psychological bias. You need to make sure that you inform people of those. And then, so you explain what's a Monte-Carlo, you explain how it's going to work, explain some bias and make sure that you're vigilant for them. Maybe it's worth it to check the assumption behind the plan and do a key assumption check, which is simply taking the time to list all the assumptions. For example, assumption A, we are able to disable the alarm system. Or assumption B, we are able to fence the goods once we have the jewelry. So you list your assumption, you list your level of confidence in those assumptions. I am very confident we'll be able to fence the good after. Good, you can write that down. And then add the third column of your key assumption check about what happens if your assumption is wrong? And just some way to take a look and be more critical about what you're putting in, so you don't take anything for granted within your model. So this is basically the few steps for facilitating the workshop. So some of the distribution you can use that are more simple, by simple is still better than a single point estimate. The first one is uniform, and we're starting with the very basic here. Uniform distribution can take any value between 2 points. They all have the same likelihood of occurrence. So typical question to get that out of someone would be, what are the minimal and maximal values this price can take? Here you see the example, and the answer would have been $2 and $30, so any values between that could fall in. And you got some variants that are continuous and some that are discrete, depending on what type of data you're trying to secure. For example, a price could be a continuous, while discrete would be a number of child would be something hopefully which remain discrete. So this is a first distribution you can get out, and once again it's just to say from what to what can you see that value go. Step up is the triangular distribution, or PERT is a variant which is similar in the way you extract the information from people. They're bounded distributions, so there's limits to them, and there's a mode being the value that's the most often represented. So a typical question for that, or questions, would be, what are the minimal and maximal value this price can take, just like in the case of the uniform distribution, but you would add what value this is most likely that you're going to reach in this distribution. So that would be your peak. So those are the questions you ask, and that's something you can have in a discussion, be it with armed criminals around the table in this smoky and dark environment, or something that you can ask to any more serious risk workshop. Here the example that we have is a triangular distribution with the values of minimum 2, maximum 30, and most likely $7. So it's something, once again, you can get, and you don't need advanced mathematics. Yes, there's limit, but this is something that can be done, and easily through any type of software that's doing real Monte Carlo simulation. Next one that we're going to take a look at is log normal with alternative parameters, and I like that one a lot, because the log normal distribution describes a lot of things that can happen, but a true log normal, to get it, you need the value of mu and sigma, which is not something you can easily get out on a table. A log normal distribution with alternative parameter just requires someone to have some insight in the problem, but not necessarily mathematics. So the first thing you can see is that it's similar to a triangular distribution, but the tail is different. And this is a very good distribution to model things that got a long right tail, like project cost overrun, for example, where there's a center of mass where most of the potential or the possibilities are, but it can reach much higher as well. So once again, this is the type of question you'd ask to get a log normal distribution out of someone, is what's the value would expect most of the time for this price? And what would be the high and low value that you would expect to see only once about every 20 times? So basically, this means that you want a P5 and a P95 value. So someone who's experimented and knows about his discipline will be able to get some sort of estimate of that. But the key thing is, it will not bound your right tail. You can go up to, you can always manually bind it, but you don't need to if there's a potential for things to go much wrong or much better than expected. So here the log normal distribution that you can see is with the value of 2 for the pessimist or the left case, if you want, 27 for the high case. So it's either pessimist or optimist. But once again, that's not the absolute high case, but it's the one that you can expect to see about once every 20 times you'd be running that situation. And then the most likely value is 7. So this is a very useful distribution. And sometimes you even have less data. And you may want to update your model, because once again, models do decay over time if you don't update them. And you might want to use a beta distribution, which is very useful. I've been using this for safety cases, for example. When you don't have a lot of information, it can help you a lot. And as you gain more information, your model will get more precise. So let's take a look at the beta distribution. It's a continuous distribution of the probability of a given binary outcome. This is quite a mouthful. So basically, you're trying to model something that's got a binary outcome. Would a traveler want an upgrade on a flight? how many faulty widgets are being produced. So the state of the widget is either faulty or not faulty. So that's a binary outcome. The number of fighter would win, I guess. The number of students that fail the test. So this is basically a binary outcome. And when you start to, we have very small sample size. It's hard to know if it's, let's say I only toss 2 times a coin. Well, it might end both on tail, even if the likelihood is 50-50 overall. So when you have, and that's an easy, the coin is typically, fair coin would be always having the same likelihood of 50-50 of going either way. But a lot of binary outcomes are not necessarily. Hopefully your widget that you're producing, once again, back to the darn widgets, but hopefully the widgets that you're building are not half of them faulty. So maybe it's 1% of them, maybe it's 0.5%. So how do you know that for sure when you have very little sample? So basically, you take that test, you don't know the likelihood, and here's an example of a beta distribution. Basically, it states that I ran a binary outcome situation 5 times. 2 times, let's say those are, we'll pick the travelers who wanted an upgrade on the flight. So I have 2 travelers, and you see here, 2 travelers that did want the update, and 3 that didn't want the upgrade. So basically, based on those 5 travelers, this is the range of likelihood that someone will want to have that upgrade once it's offered, maybe for a minimal fee or something like that. So it's fairly wide. And let's say I've got more data now. I keep asking customer, do they want an upgrade or not? And I've got a bigger sample here. So the second distribution, it's still the same distribution. It's a beta distribution, but instead of putting 2 and 3 because I only ran 5 times, here I have 20 and 30. So I've got 20 passengers who accepted the upgrade minus a small fee versus 30 who declined it. So now what I see is my range was what before I had 90% of having the real likelihood between 10% and 75%. Now it's getting much narrower. I've got 90% chance of being between just about 29% and 52% of customer who would accept the upgrade. So now it's more precise. It's just bigger sample, more precision. And that's something you can use if you're doing an inspection program, for example. As your inspection program evolves over time, you're gonna have more data to put in your beta distribution. And once again, it's a super simple distribution to be using because you're taking binary outcomes, your alpha and your beta, so number of people that accepted the upgrade, number of people that did not accept the upgrade. You put that in your function and you get your distribution out. And as you increase, I'm going to pass to the next slide now. As you increase, you see that in red was 2 and 3 customer, in blue was 20 and 30. Then I incrementally added to 200 and 300, 2000 and 3000, and so on. So you see that as I go, initially my 2 and 3 was a very wide distribution, but the higher sample I've got, the more precise and the more solid my conclusion is, if there's nothing underneath that can change over time. Let's say, for example, that you don't offer the same possibility, it could change your outcome. But as it grows, your sample is going to get more and more precise until you know very precisely where you should be standing. For example, at 20,000 and 30,000 cases, you'll know that you're exactly on that 40%, which is your theoretical value for that situation. So it gives a good idea. It's something that's easy to add as you just add the case as they go on. So I've inspected more widgets. I've got more information. Add them to your model, and you're gonna have a more precise answer. So basically, there's a Bayesian field where you update the prior probability based on either new data or better insights that you develop. So this is key, and I think Bayesian statistics is the way to go forward for risk management. It's something that we'll see more and more over time. So one more distribution, which will be the Poisson distribution. But before we start talking about how to apply the Poisson distribution, let's take a look at when should we use it. So let's say I'm asking myself the question, how to assess the likelihood of having a security guard patrol at the wrong time. This is the example for a heist, but it could be the same thing about when a pump is expected to cease operation, or when could we expect new customer to call in a customer center, for example, a call center. So there's multiple situation where you want to ask your question about, I know that something's happening at a certain frequency. What's the likelihood of that happening precisely when I want it or don't want it? So first, so in our case of our jewelry store, let's think about maybe they got a contract with a security agency that conducts patrols, and those patrols, they're random to prevent the scheduling of heists with their scheduling of the patrolling, obviously. So you want to assess what's the likelihood of having a patrol showing up at my specific time when I'm doing my heist, for example. But once again, in less ridiculous example, it could be when should I increase my level of people in the call center, for example. So let's say that the service of the security agency is based on an average number of visits per night. But it's possible that some night they have 0 visit and some night they have more than 1 visit. So maybe it's not the contract doesn't stipulate they're going to pass once per night, but it's random. But on average, over the whole year, they want to see that they have an average of X visit per night. So once again, it's a very common problem. Let's see how we can solve it. So how do we know if the patrol is arriving exactly when we're committing the deed in that case? So the Poisson distribution is to model discrete event over a period of time. Initially, the first time it was developed, it was for people getting injured by horse on the battlefield, but it can be used, obviously, our statistics can be used for multiple purposes. So basically, it's a distribution that's defined by only one parameter. If we recall, for example, our triangular distribution we're talking earlier was defined by 3 parameters. And a uniform distribution is defined by 2 parameters. Well, that one is only defined by lambda, so only one parameter to define this specific distribution. And I'm going to show you what a lambda of 3 looks like, and then we're going to have the discussion about how to calculate lambda. So basically, a lambda of 3 for a Poisson distribution, as you can see on the screen at the moment, states for my period of time that I'm considering how many times the event will happen based on a lambda of 3. So it shows that in some case, about 5% of case, it means that you won't have any visit from the patrol, or if it was the patrol or having calls to the call centers or things like that. And the other extreme, you could have up to 8 or 9. It's not possible to have more, but this is the most likely values here. And basically, you would have most of the time 2 to 4 of the event happening with a lambda of 3. Basically, it's kind of an average of the situation happening during your time period. So how do you calculate it? First, before we calculate it, assumptions are super important, and a lot of people run statistical tests without asking themselves, am I supposed to be running that test? And those assumptions are key, because if not, your test is basically garbage. So the assumption for Poisson distribution is that the average rate of the event is constant. So the average is not the event, so you don't know when it's going to happen, but you know that it's constant, that once every night or twice every night or every 2 nights, no matter what, you're going to have the incident or the event happening. So that's the first assumption. The second assumption is the events are independent of each other. So it's not because you just had a visit that they will not revisit again in the same night. So the events are independent from each other, and 2 events cannot occur exactly at the same time. So if you have a very bad patrol schedule and 2 or 3 teams, they could happen at the same time. But let's say that in our case, they have one safety guard, security guard, let's call him Joe. So Joe is passing from one location to the other randomly. Those are the assumptions for Poisson distribution to work. So how do you calculate lambda? It's fairly simple arithmetic. So the number of time the event happened over the time period. For example, if you're looking at 30 nights, you do 30 nights times, let's say, 8 hours. And how many times the jewelry store was visited by that patrol over that duration. And then you multiply this number by the time period you're interested in. So let's say that I've got a 60 minute on the site. Well, this is the time period I'm interested in. I don't want to be interrupted by the patrol while I'm doing this. So this is providing your lambda. So this is what you have here. Basically a distribution, a Poisson distribution, where the lambda of 0.125 would state that you have about 12% chance of being in a situation where while you're conducting a heist of a 60-minute time period on location, you've got that 12% chance of having the patrol just randomly passing you by. So this could be used in reliability. This could be used for many problems. Once again, it's not a complicated distribution to get. You just need to understand how you calculate that lambda, and then you pick the right distribution for the model you're running. So we're going to use all those distributions that we've just covered within the demonstration. So without further ado, I suggest we jump in model risk for the demonstration. I'm mostly a at-risk user, but I wanted to use a solution which provides a free solution. David Vos has been kind enough to provide a free version of model risk to users. It limits some of the functionality, but you can still do a lot with it, and it's a good way to start playing around with models. So that's why I wanted to remove the cost of entry into modeling by removing at risk from the equation. So I'll be using model risk for that demo. You got to keep in mind that I've got about a total of an hour using the software, so it's going to show how intuitive it is if someone as dumb as me is basically able to operate it. So stay tuned. We're going to start. I'm just going to switch to the software now for the demonstration portion. So it's time to jump in model risk and take a look at what can be done modeling wise. So as you can see, it's an Excel file. Model risk is an Excel add-on, just like at risk, where you can add directly within the cell some more functions such as distribution and outputs from Monte-Carlo simulation. I'm using, once again, this is a trial version, so I've got some of the functionalities that you'd get from the full version, but I'm adding as well all the logic that I'm putting in there you could replicate without having the full version. The full version is just adding more stuff and things that makes life easier for a lot of that modeling. So first scenario that we have is a smash and grab. So when we take a look at it, remember when we did the layer of protection analysis, high level for this heist, we identified layers of control. Now we need to make sure to bypass those layers of controls by using some techniques, and based on those choices, we'll have different likelihood of success. For example, we've got smashing the outer layer, which could be ramming the joint with a truck, smashing display A, B, and C. You'll note that we don't care about in the alarm system in the smash and grab. The reason is you're hitting fast, pulling out fast. That way you don't start fiddling with the alarm system. You just assume or hope you'll be quicker than the cops. Then there's the exfil phase where you leave with loot. And based on that, basically, I've listed the assumption. Those assumptions you'd get from the workshop as you talk with people. And for example, you got here smashing the outer layer would take between 30 seconds to 2 minutes. Maybe you need to ram once or twice. Maybe there's some debris that needs to be taken out. So that leads to a uniform distribution, as I have only 2 data points in there. So that's something you'd get around the table, or based on your experience or the experience of the subject matter experts you have around the table. If they don't shoot you, basically, because it's a robbery. You can't trust those types. So smashing the displays takes between 1 and 2 minutes, and there's a most likely value of 1 minute and 20 seconds, basically, that we are expecting. So this is really a triangular distribution. We could use a PERT as well, but so again, either you put the distribution in by typing it within Excel, it's the logic itself, or you could just, in the model risk tab, just click on select distribution, and then you can choose one of the numerous distributions that are there, and you would add the parameters. So if I'm going for a triangular distribution, for example, I'm going to go for a triangle, and I just put in the parameters straight there. So it depends on how at ease you are with the distribution, basically. So I've got the 3 displays that I'm planning to smash to extract the jewels. I've got the exfil time, and then I've got the time on location based on 3 options. Either I'm staying in place and I'm grabbing 3 display, or I'm doing 2 displays or 1 display. And basically I'm putting the value of each display. In this case, I use exactly the same formula. There's between $3,000 and $20,000 per display. And I've used uncorrelated here, and we could correlate those displays, the value of them, because it's realistic to think that a high-end jewelry store would have similar value per display, it's rather than having one very cheap and two very high. The thing is, if you don't correlate some risk in a model, it's going to have impact on your results. If I'm having a lot of correlation, the spread of the model, the final output, will be wider typically. If there are positive correlation, because things will move together. That means that I'm more likely to have the tree counter, if they're all correlated at a high value or low value, so it spread the distribution. Well, if I don't correlate things, typically you'll have those tree counter converging toward the mean, because they're all having the same formula. They're not correlated, meaning that you'll have maybe one high, one medium, and one low every time, or something like that. And that's going to make it so that that total value will be centered, which has a bigger impact on the tree display heist than the one display heist. So we have this. We need to take in consideration the opposition, so the cops. So what's happening with the cops? Well, they have two activities that feeds into their total reaction time. So I've got the first one here is the time for the alarm system company to contact the police. That's the first step. And then I've got the time for the police to respond as a priority one to that call, if it's a priority one, maybe not. And once again, you list your assumption. In that case, that's the assumption for the company to see, well, okay, it's not a false alarm, so I'll reach out for police. And here we have the police response time that you could get. Sometime it's public because there's a public administration target about police response time, for example. So all that will give you some information, or maybe you time some events, or you know someone at dispatch who can tell you whichever way works for you. But here we're using a Vos log normal distribution with alternative parameter, stating that my scenario where I see only once every 20 times I can expect only 1 minute for the response, and only once every 20 times is going to be worse than 12 minutes. So it gives an idea, and it leaves room for a tail end. Maybe that police is busy, maybe that they got a lot of calls, so it leaves some wiggle room as opposed to capping this with a triangular distribution where you say, well, nothing can be more than 12 minutes. Which will not be super realistic. Although police response time are pretty awesome in major cities. Then we've got the total reaction time. And in this case, this is a very short one, but every time I'm hitting F9 to refresh, I'm getting new values out of this. And what I have here basically is some logic, because once again, if you're using a tool like Model Risk, you're doing real modeling as opposed to pretend modeling where you only have lines and it's adding up. Here you can put some logic. So my logic is, if my time on location exceeds the response time, I'm busted. If not, I've evaded police. And as I go, we can see that eventually, of course, just doing one display typically has a smaller response time, and not response time, but a smaller time on location, which means that I've got a greater chance of evading if I'm doing only one display. But then my payoff will be smaller. Once again, typically, it's going to be smaller for the reason that I'm only doing one counter and I'm not doing all the counters. So it just gives an idea of what you can expect as far as results. So what we can do now is we will take a look at the how much cash can you expect from that. I've already run the model. So what I'll do is, typically you'd run the model. And since it's the free version or tryout version, there's some delays involved. So I've already run the model, but if I hit results and I'm gonna pick up the cash, for example, time on location, I could compare how much time I'm passing on location per counter. So it's interesting, but in my case, what I want to see is how much cash can I grab out of this. So if I'm doing the tree display, well, you see a very high likelihood of getting caught, because basically I've put some logic saying that if you're busted, you're not getting cash. So tree displays lead to nearly 70% chance of being busted, and then you got the value of about 30 grand, 40 grand, something like that is the expected outcome if you're not getting busted. If I'm going with two displays only, well, I've already dropped nearly 20% of my likelihood of getting caught, but I'm getting less cash. It shifted my profit curve down. If I'm only doing one, okay, it's a much better outcome, but then I am getting between 4 grand and 20 grand basically out of that heist. So it's probably not worth it. Maybe I should be looking at something else to be getting my cash out. Because then for this strategy to work, I'd have to execute a lot of heists to hit my target of 150 grand, and trying to do all those heists every time. If I got a chance of getting caught of nearly 30%, well, after a couple, I'm fairly sure I'm gonna get caught. Plus this, you need to understand that models do decay. So there's, as time passes, technically speaking, you should try to refresh it. And well, the thing is, eventually the cop will develop tactics, or the shops will develop tactics and change their strategy or approach, and may have a higher chance of getting you if you're starting to do a series of smash and grab, for example, using that modus operandi. So this is the first option. Let's take a look at the second option now. So the second option was to go for a burglary. So let's go with the burglary scenario. Just open that up a little bit to give us a chance. So basically, for that, we have the crooks and we have security once again. And this is where we'll be using that Poisson distribution and those beta distribution. So let's focus on the activities, assumption, and distribution of the crooks. The steps to do in that case, it's a night burglary. It's a little bit more like a heist. So you need to disable the alarm, maybe with a hacker or something. Let's go crazy with Hollywoodian stuff. Then we gonna gain access to the building. We need to do it in a more discreet fashion because we don't want to make noise, because then we attract attention. So it's not like we can just ram a truck in there. So it's gonna take more time. Let's pierce the safe and do the magic on it to open it up without tripping the silent alarm, which is in the safe, to make things exciting. What's the time to pierce the safe? That's going to be useful to evaluate if we're getting caught by a patrol. Exfiltration, similar to the other one. How much cash is in there? So let's take a quick look on those. So basically the success to disable the alarm and to not trip the silent alarm on the safe. I've used beta distribution because typically you probably won't have like someone who claim, yeah, I've did that 1,000 times. So you have little data. So this is one of those instances where here I've put for the hacker, he tried it 9 times, 5 times with success, and 4 times where it didn't work. So he didn't disable the alarm. And for my safe cracker, he tried it 10 times, 7 times it's a success, and 3 times it's he did fail and trip the alarm. So basically, it gives some idea, and one good way to de-risk this would be to increase the ratio of success versus failure. So if you could practice, for example, on a simulator, on the other alarm system, and get better at this, maybe he could decrease the risk. Because with only 9 or 10 cases, once again, if we recall, it's going to make for a very wide distribution of potential likelihood for that hacker and that safecracker to do to apply their craft. So this is for the beta distribution, and then you get the time. Once again, I've used triangular distribution for the time here and for the time for pierce the safe, simple distribution, and uniform distribution with only 2 points of data to simulate the exfiltration. So depending on how much information you can extract from your expert in your workshop, you'll be able to put more or less. Then there's the loot, how much cash, and that's a big safe. So there we won a lot of money. So remember, our target was 150 grand. So what we have here is a log norm alt distribution, saying that 1 case out of 20. So that's on the bad side. There's only $36,000 in that's safe, maybe in jewels and in cash. And then in 1 case out of 20, because it's the 95 percentile, I'm gonna get at 350 grand. Using a log norm distribution gives us a nice fat tail on the right, which can say that maybe there's a big art show in town and they got more stones, for example, or they're a distributor and they just receive a lot more money. So it gives some room for those good or bad outcome at the right. And I've added a minimum value of $80,000. There's always money in that safe, or there's always gold or stones or something like that. So this gives us the loot we can expect. And going from, so that's for on our side for the crooks. Before we go on likelihood of success and value of the heist, let's go with the security team. So we said we'd use Poisson distribution in order to evaluate what's the likelihood of having one of those random patrols hit us at night while we're here. So if we recall, to calculate the Poisson distribution, there's only one parameter, which is the lambda, which is calculated by using the following formula of the average number of event divided, so the number of events divided by the duration of the time period where you did your observation, and then you multiply this by the time you're actually exposed. So let's take it step by step. It's going to be clearer. So I've got one patrol per night. So one patrol on 180 minutes. So that's the first part of my statement, times the time I'm going to pass on target, which in our case comes from 3 distribution of time to gain access to the building, time to pierce a safe, and time to exfil. So I'm using those 3. So this value here will change the time and location every time I'm running it. And this in turn will change my lambda. But and then out of that, it's going to feed within the Poisson distribution to see, okay, what's the actual likelihood of facing a patrol. So if I go with, I'm going to go with result and Poisson distribution. Once again, I ran this already, but you all seen monte-carlo simulation running at that point. So basically it states that I've got nearly 90% chance of having no patrol during the time I'll be there. I've got about 10% of having 1 or 2 patrols. And let's say that every time a patrol comes and see me, he catches me. So what I'm doing, what I did is I used logic. Once again, I used simple Excel logic, and that's things you can't model if you're using a solution like Active Risk Management Manager, for example, ARM or SWORD from SWORD. Basically, it's good for certain things, but it cuts down on the flexibility on what you can do and what you can't do. To integrate risk into business decision, well, all your financial analysts are using Excel, so you might as well take something like at risk or model risk and put it straight in their document. It works better. So the simple logic I've put is if G25, which is my Poisson distribution, exceeds, if I'm higher than 1, basically, it's gonna state I found something. I was found. So it's a fail, basically. And I've added here on detection likelihood, not only the presence of the patrol, but also of tripping the silent alarm. So you combine both. And this will give you a status of either busted or evaded, like we had previously in the smash and grab scenarios. If I'm taking a look here, that's an interesting feature that calculates, after you run the model, some statistics. That's here it's the VOSIM probability function, which gives you basically what's the likelihood of having a patrol finding you. It's going to give you a percentage. So it's take the distribution, the output after you run the model, and you can identify what's that percentile 50, for example. That would be another function called sim percentile, but sim probability will give you what's the probability of hitting a certain value. In this case, what's the probability of having higher than 0? It's 10.48% chance. So 1 highest out of 10, you'll have the patrol go and find you. So when you add this to the likelihood of tripping the silent alarm, and especially with the current stat, which we don't have a big sample, it makes it pretty risky as an operation to do. And this is where we have the likelihood of success, of succeeding, of realizing the heist, and we've got the value of the heist. So let's take a look at the value of the heist, excluding the fence fees again. But this is where we have, you see here, you can right away say you've got less than 45% chance of getting caught, but you still fairly big bit, if depending on how you take a look at it. So we could go with the sliders once again. This is one of the versions I prefer. I'm more used to the way at risk works for that. I think at risk is cleaner for that, but that's probably the only thing I prefer at risk now that I saw modular risk a little deeper. So you could hit, for example, as we know that I'm putting 0 in my logic if I'm getting, if it's a fail or a bust. I could just put this here and put my 150 grand target here. And I know that I'd have roughly 17% chance of hitting my target in one go, so that's good, and I'd be able to take a look at what's the likelihood, the exact likelihood of failing the heist. So those are good things coming from this. Another important thing is using the tornado chart. I'm gonna go quickly for smash and grab on that one, and I'm gonna take my 3 counter payoff and I'm gonna do result once again. And I'm gonna go cash value, and I'm gonna insert a tornado chart using all the variables. It's good. And this is very interesting. The tornado plot will give you what are the biggest contributor to your risk. So one of the things that you do with that is you can see that for a smash and grab scenario, sorry, I took one display. So for one display, the value of the display is the biggest contributor to the variation of your success. If you're taking a police response time is your second variable. So if you're looking at the big bucket item you want to mitigate and work on to maximize your profit or minimize your chance of getting caught, those are the top one, while you should not be worrying about the other smaller ones. If I'm going instead with the 3 cash value display, it's just recalculated. And how interesting, now police response time is the biggest driver because, hey, guess what? Your risk is much higher, and yes, the displays are important, but police response time is what's going to get you most of the time. So if you want to mitigate this is where you start thinking outside of the box of, do I want to put more counter smasher so I'm quicker to extract the loot? Or do I want to create a distraction for the police in order to make sure that they go to the other side of the town or their territory, and or there's a bigger priority somewhere else and they let you go. So this is where you can start thinking about what's the cost of that mitigation, and then you can resimulate this and see by how much you reduce your risk and you get the value you get out of your mitigation plan. Good luck doing that with a risk register. So that's the sort of thing you can do once you start thinking in models. Last thing I'm going to take a look at with you is I'm going to get back here. I'm going to get, and I could just do it straight in the window once again. I've got 2-3 hour max with that software. So it shows if someone as dumb as me is able to operate this that quickly, means that it's a very good software. So we're going with value of the heist. I'm going to get back to my histogram. I'm going to remove this. I don't want to overlay. And we see that once again, there's a high likelihood of getting caught, but after that, there's good profit. And if I'm getting to here, that's the opposite of what I had. Here I've got still fairly high likelihood of getting caught, but the payoff are much smaller, meaning that this is a low yield, medium risk strategy. If I want to do multiple smash and grab, it's a low yield, medium risk, or even high risk in some case, if I'm going with the 3 display smashing, for example, as opposed of the burglary, which still got a fair bit of risk, but the payoff is much bigger. So you might only need to conduct 1 or 2 in order to get your 150 grand, and the risk would be lower at that point. So that's the sort of thinking you can do once you start thinking in model. Last thing I'll point out is I've done a lot of basic out-of-the-box Excel logic here. One thing is, if you want, by using the paid version of Model Risk, you've got functions like aggregate, which enables you to do much of that work directly in one cell. Usually, I'm trying to put things in long form most of the time for model because it's easier to point and explain to people. And there's a limit to the understanding of people if you got like 5 or 6 nested if statement in the same Excel cell with the addition of funky formula from your risk simulation software. So at some point, sometimes it's easier to spread things out, but you've got function like aggregate monte-carlo from Vos is a little bit like the, or actually quite a bit like the risk compound from at risk from Palisade. So if you pick aggregate Monte-Carlo, what you can do is straight, without it doing any funky logic, I could go with Vos binomial, for example, if I want to have a frequency, something which is hit or miss, something that happens or is not happening. I want 1 try at 50% likelihood. And then I'm going to do the impact, let's say cash, but I'm going to do Vos, normal, for example. And I'm going to do an average of 100 and a mean at 100 and a standard deviation of 10, just like IQ. And basically what I'm doing here is I'm putting the first parameter is the frequency distribution. So what's the frequency of that event happening? So here it's 50% of the time you got 0, 50% of the time you got 1, because it's a yes or no situation, it's a binomial. And then severity distribution, or that could be like your consequence. You have it here, so that's your normal distribution. And the aggregate distribution say that 50% of the time your value is 0, because you have this in your frequency. But when the risk does materialize, here's the potential impact. So that's really useful, and that beats matrix by a lot, because by doing something like that, you can basically create your full range of likelihood and your full range of impact together. And once again, as you can correlate those things, you can go into fairly comprehensive and in-depth models. So just once again, an example of one of the cool features from the software. You can go much further than just pushing a standard heat map, which it's not really that useful. Once again, Hubbard and other thinkers are proving it's not the best approach, it's not best practice. It takes time, but I think really anyone that start with a free version, take model risk free version or start coding. You can do a lot of this in vanilla Excel, Analytica works, whatever is your poison, just pick one and start experimenting with it. And it's going to become more and more natural, and it's going to give more value for your shareholder and stakeholders than just talking in yellows, greens, and red or orange, or things that don't provide much value to the business. Because once again, here you got the cost, you got the cost and the impact of the mitigation. You can wrap this all up together. And really drive some value for decision making. And this is, once again, we're there to prevent the auditor to take over. We're there to make sure that the board is comfy with what's being done, but we're mostly there to make sure that we support decision making, and that's the fun part of what we do every day. So let's get back to the PowerPoint quickly. So I do hope that the demonstration was useful, and if you're not used to model, that you saw the power that you can have when you're doing a proper Monte Carlo simulation in order to understand your risk. A few key points. First of all, models are a better way of looking at risk and their effect on your objective. When you're doing a model, you're forced to take a look at what's the actual usefulness of your controls, and what are the causes of the underlying risk, and what are the assumptions you're putting in there. So it's a completely different way of doing a risk analysis than just having a register and putting some stuff in there. There's some value in taking the time to think about risk, but I think that model is just stepping things up and making it better. Also, you have more data than you know. We saw the beta distribution, which you can use when you don't know a lot about your situation, because you don't have that many data points, but it enables you to refresh and update the model by just tweaking the parameter of the distribution, so eventually you get a much more precise understanding of what's your real exposure. So you do have data that you can leverage. Also, even if you don't have all the data, it will still be a more useful endeavor than single point estimate if you're doing a model, because basically what you're using is ranges. And theoretically, it should be easier to come up with a range than coming up with a precise number. And if you're using the proper software, if you're doing a real Monte Carlo simulation with model risk, at risk, whichever is your tool, where you can model the actual logic, you integrate the risk management directly within the tools of your peers. You're working with the finance team, you're working with the marketing team, the operations team, and then you're able to directly interface with what the tools they're using on the day-to-day life. So that there's a lot of value in doing that. And also dive in. I mean, you gotta try. Of course, it looks much simpler to just go with one of the off-the-shelf solution, which just put all the risk in big, colorful heat maps, and it's less thinking. So it's reassuring, because you say, "Oh, I'm doing my risk management, check," but it's not actually helping your business. So might as well dive in, take the time to learn. Take a free tool and slowly build from simple model to more complex model. Make sure you got mentors, or you're taking classes, or you get something to keep you progressing into the proper risk management. But you should dive in. You should give it a try with something small, and then you can grow it. One of the model I've done was just for a very small benefit analysis of which contracting model we should do for a very small purchase. But once again, you gain experience, and you grow and you get better at it. So you need to try. and don't commit crimes. I mean, it looks good, maybe that 150 grand tent is tempting, but no, just say no to crime. You're better off being a risk manager or just being in business and making sure that your risks are lower in order to reach that 150 grand task. So thank you very much for your time. Thanks, Alex, for all the work you've been putting in place. And thanks to the wonderful speakers that are part of Risk Awareness Week 2020. I think it's a great event. I encourage you go and take a look at what's out there. There's some very, very interesting things or thoughts being brought forward by some of the leaders in the industry. And it's a great way to keep on evolving the discipline. We should not be doing old stuff like from the 80s with those heat maps. Let's keep evolving the discipline. So thank you. Please feel free to reach out on LinkedIn, and I'll take a look in the question from this webinar, and I'll answer every single one of them. So thank you very much. Stay healthy. Be well.